Hello, today we're going to cover Newton's laws. There are three of them, and you've technically covered two of them already, or you know of two of them. In this video, I'm going to cover the first two, and then the last law we'll cover in another video. So Newton's first law is also known as the law of inertia. So the law of inertia. So what does that mean? Well, mathematically, the first law is essentially this: F net equals 0. So in the physics world, what does that mean? Essentially that there's a lot of forces and they all balance out to 0. So you can actually have an object like an eraser, and I have two forces and it's not moving because my fingers are pushing equally on either side. And then of course I could have other people pushing, and then also there's gravity pushing it down to the ground, and then the normal force pushing back up due to the table. So all of the forces are balanced, or there's no one stronger force than the other, and therefore F net is equal to 0. So as a result, the object either must be at rest, or, this is really important, at constant velocity. At constant velocity. This last part at constant velocity is a little tricky because a lot of people think, okay, if I'm mowing the lawnmower, I'm still pushing it. But you'll notice the lawnmower is going at constant velocity. And so even though people think they're pushing it, there should be an applied force, which there is. But they forget that there's a force of friction pushing back, which causes the lawnmower to go at a constant speed or constant velocity. All right. And so that is a law of inertia. So all things continue at rest. So it must be at rest or constant velocity because all the forces are balanced. So let's do a quick example of an object at rest. We're going to do a free body diagram of your water bottle sitting on a desk. So here is the top of the desk. We have your water bottle. Okay, it looks more like a weird looking bottle, but sure, good water bottle. Let's say the water bottle with the liquid is 2 kilograms, which is actually a lot of liquid. That would be a 2-liter bottle. All right, so what forces are on this? Well, technically, there's gravity pulling down on the water bottle, and then the normal from the desk pushing back up onto the water bottle. So if you did your F net equation, F net in this example is equal to 0 because the water bottle is at rest and A is equal to 0. And so when you fill out your formula, your force equation, then you have Fn, remember that's positive, minus Fg because Fg is down. And therefore Fn will balance out and equal Fg. So that's the easy case. Most people understand the case at rest. The next example will be the case at constant velocity. All right, so here's an example. You are pushing your chair, and you can do this at home, which is perfect. So to help you to visualize, pretend the chair is 5 kilograms, and you're going to push it across the floor at a constant velocity. There is a force of friction because you can hear the chair rubbing against the floor. If you have a carpet, it's very difficult, so you got to push against that carpet, and so that is the force of friction. All right, so there is a force of friction, sorry about the ring, that is 10 newtons. So we need to calculate the applied force and the normal force. So let's draw that diagram. So here's my chair. And there's the floor, and let's have you pushing onto this chair, and you're walking away like so. It is a very bad looking diagram. Okay, but good enough. Okay, perfect. All right, yes, very bad diagram, but that's all right. let's figure out the forces here. We have gravity, which actually pulls the chair down. Then the floor pushes the chair up, and that's the normal force. You have yourself that is pushing on the chair, which is the applied force, that's you. And then you have friction from the floor. And I want you to try it at home. You feel that friction on the floor pushing back. So you can't actually just push and the chair just speeds up forever. There's a constant velocity. You're going to push it at a constant velocity, right? Now, when you analyze horizontal and vertical components, just like in projectile motion, vertical, then you will notice that F net is going to be equal to 0 for both cases. F net equal to 0 there, and F net equals to 0 there. Why is that? Well, the chair horizontally does not move anywhere. Well, it does move. It's just it's moving at constant velocity. So A is equal to 0. Now, vertically, it doesn't move anywhere. So vertically, it's at rest. So F net equals to 0 for horizontal is technically a constant velocity type motion, whereas vertically, it is at rest because the chair is not sinking into the ground or the chair is not floating off the ground. So it's definitely at rest vertically. Okay. All right, let's actually write out the F net equation or the force equation. And so what we got here is F net is equal to 0, and this is going to be FA minus FF. Notice FA, we decided right is positive and left is negative. When I plug in my answers, all I have is FA minus 10, and so now FA is equal to 10 newtons to the right. For vertical, what we have is something very similar. F net is equal to 0, and that is equal to Fn minus Fg. Remember, Fn is up, Fg is down. That's why this is negative. Let's plug it in. Fn minus mg, because we're just going to calculate what the force of gravity is for that chair. You can actually write it like this if you like, and then we have the mass times 9.8. So Fn in this case is equal to 49 newtons, and it's heading up. All right, let's do Newton's second law. Newton's second law is essentially this: F net is not equal to 0. F net is equal to ma. Pretty easy laws, right? Like I said, you already been doing these two laws for the last several days, so now we're just going to officially label them. So this here is when the object is actually speeding up or slowing down. All right, so the object is speeding up, so you can make something go faster, or you can push something to make it go slower. So the object is speeding up or slowing down. All right, let's do an example of, I got an idea. Let's do this. All right, here's my example. You want to lower a bucket of cement, which will take less force. So option A, lowering at constant velocity. Notice this will be a first law question. And then option B, lowering it at 1 meter per second squared down. So this would be your first law option, and this would be your second law option. So which one will take you less energy or less muscle, less force to do that? Okay, so we're going to set this up. Oh, and I guess I should write down the mass of the cement bucket. So you want to lower let's say it's 10 kilograms of cement in the bucket. All right, we're going to do option A and option B. So let's do option A first, and then we'll do option B over here. All right, option A. I'm going to draw my little bucket of cement. So there is my bucket. And let's draw our forces on this. You're going to hold up the bucket, which is applied, and then you're going to have gravity pulling down, and you're going to lower the bucket very slowly at constant speed or constant velocity. So A is equal to 0. Perfect. So let's write out the Fnet equation. Fnet is equal to 0, and in this case, Fa minus Fg. Remember, Fa is up, that's why it's positive. Fg is down, that's why it's negative. All right, let's plug the rest in. We have 0 is equal to Fa minus Mg, and Fa is now equal to 10 times 9.8. And now Fa is 98 newtons up. So for option A, it will take you 98 newtons to actually pull up on this bucket. And so let's check out option B. Remember, option A is your first law, and option B is the second law. All right, second law. Let's draw a free body diagram first. You always draw a free body diagram. So here's my bucket again. Again, I have Fa going up and Fg going down. Now remember, the difference here is the acceleration is now down. So how you're doing this, you're going to actually lower the bucket, but you're going to speed up the rate of this. So it's just going to go faster and faster, just ever so slightly. The bucket's not falling, but it is going faster towards the ground. It's not going at the same speed. So it's going at 1 meters per second squared going down. All right, so what would that look like? Fnet is equal to ma. Remember, it's the second law, so it's not equal to 0. And then you have Fa minus Fg. All right, so let's plug things in. This is 10. Don't forget it's minus 1 for the acceleration. Fa you're trying to solve for. And Fg, well, technically is mg, so it's going to be 10 times 9.8. This is going to be negative 10 is equal to Fa minus 98. So Fa is going to give you 88 newtons up. So you'll notice that it is actually gives you less force. You need less muscle to actually lower this if you're kind of lowering it in such a way that it speeds up, right? You're not gently lowering this at constant velocity. You're kind of almost, well, not dropping it, because if you drop it, it's at 9.8, but you're kind of like a mixture of slightly dropping and lowering it, and so therefore it's going to take you less force.